Using stoichiometry to calculate equilibrium. As you can see here, we have moles and we have liters for just the reactant. So I'm going to be putting a concentration area over here where we have C is equal to N over V. So we're going to be doing that for our compounds over here. We end up getting 1.74 moles per liter. Same thing for Cl2, and obviously we don't have anything for BrCl because this is our product. It's not mentioned in the data yet. It hasn't been produced yet. Okay, so initially we have a concentration of 1.74, 1.74, and 0. Again, I've disclaimed here that this is all going to be in moles per liter. C stands for change. Okay, so is there any change going? Well, we have a value of X to be our variable. It's going to be a negative for both our reactants because both are being used up, so it's going to decrease. And of course, our product is going to be a positive symbol as we've written here because it is being produced, it is gaining. Okay, so of course we have to put a 2 in front of the X because obviously we have a coefficient of 2 here, so 2 moles. So of course we're going to just put E as equilibrium as a sum of the I's over here and the C's, I's and the C's over here, and then the sum of the I's or the C's over here, and then that's it. So now we're just going to be putting them all into our equilibrium constant expression. See my previous video in the link in the description if you have to understand how this expression works. Then obviously we're going to have to finish up our blank over here. We have these two reactants that are multiplying each other on the bottom, and of course this can square, then all of these have to square as well. Well, 1.74 minus x times 1.74 minus x is technically squared as well, so you can just square all of them, okay, all three of these. So you end up getting this is technically over 1. You just cross and multiply these fractions, you end up isolating x on its own to be 1.27. You put that 1.27 into the x's here in the equilibrium chart, so you end up just getting 0.47, 0.47, and 2.54. Again, all of these need to be in moles per liter. However, we're trying to find it in moles, so you have to multiply by 5 liters, cancel out your liters, so you end up just getting moles. Okay, so you end up getting 2.35 here, 2.35, and 12.7 moles. Let's look at this question here where we don't have a perfect square because obviously we have a reactant here on the bottom that's not going to create a perfect square. So what are we going to do? We're going to expand it. We get something like this, and then we're also going to be putting all of them here on one side of the equal sign so that we can use the quadratic formula. Okay, so once we use that, we have a value, b value, c value, put them all into the quadratic formula equation, getting x is equal to 6.47 and x is equal to 1.041a. We are not going to use x 0.47 because this is impossible. This value exceeds the initial concentration of the reactants, which is not possible. So we have to use this one where it doesn't exceed, so this makes sense. So we're going to insert this x into these ones over here. What do you end up getting for the concentration of SO2? 2.108. This one you end up getting 1.0982, and this one here in the 1.0418. Okay, and all of these is in moles per liter. That's the answer. Okay, try this question. This is the green question of the day. Pause the video, try it yourself, and I'll be giving you the answer shortly. This is the answer.